4mm offset, apply, and that should be everything. Let's have a look from the front. So we'll be loading it down here, and these will be holding it in place. The width 40mm is being tested. So this will be the composite material. These will be aluminium, these will be steel, but we'll take care of the material properties once we get to ANSYS. However, and let's save that. File, save as. We'll call it short beam test. There are two planes of symmetry here. We have this plane of symmetry, which means that that solution will be the same as that solution, and we have the xy plane again, so that backwards and back and front will have the same solution. So technically we only need to solve 1/4 of this, and then we can extrapolate to the other parts of the other quarters of the problem. So how do we do that? Let's go. What we're going to do is we've saved. We're going to create a new part. Standard millimeter. And click derive. If derive isn't on this menu, it's also found on the manage menu. And we're taking the assembly file. Open. This button we want, maintain each solid as a solid body. So we have a new part file, but although it's a part file, it's made up of various other parts. Now the assembly file is where we started. But I said the part 3 is no longer an assembly. These are the pins. The core. It's always useful to name things. Skins. So, front. One of our planes of symmetry is the XY plane. Let's just create a sketch. And extrude. Let's see if I can remember how to do this. 1. And we want intersect. Okay. So we've effectively cut our sample in half. And we want to do the same thing again with a different plane, this plane. New sketch. Extrude. We need to go 30mm. Intersect. And solids. 1. 1, 2, 3. And and it's ignored me. So whether you cut or intersect, it's up to you. But what we've left with now is 1/4 of the original model. And because it's been cut like that, we only have the colours on the outside. File, save as, we'll call it SBT quarter. And that's the thing we need to test. So let's go to ANSYS. Get our static structural. Geometry. SBT quarter. Now before we do anything, this is a composite thing, so there are going to be 3 materials. Very different. We've got steel built in, we'll use that. We want to add in more materials, so let's go to general materials, add in aluminium, not too fussy about which. Add. But there's also a composite materials database, lots of epoxies, and what we're going to use today is honeycomb. So now we have our 3 choices of material, and the thing to notice at this point in time, more important than anything else, is the directions of the Young's modulus. Honeycomb is easy to collapse in 2 directions, but the 3rd direction is quite stiff. It's not as stiff, of course, as solid steel, but it's still impressive. So these are the 2 directions given, I think, arbitrarily low stiffnesses, but they're very much smaller than the key 3rd direction, which is in the Z direction. So that's important. So let's go away. Model, edit. So, geometry, we got pins 1 and pins 2. Let's give them their proper names. Pins top 1 is at the bottom, so let's call it pin bottom, so we know what it is. There's the core. Now ANSYS does have a much more sophisticated composite modeling package, but we're just looking at the simplest form of modeling composites today. Now we know what they are. Pins top and bottom, they are structural steel, that's fine. Skins top and bottom, we can make them aluminium. And the core, we're going to make honeycomb. Now, the thing to remember about the honeycomb is that one direction is critically important, and it's the Z direction, which we expect to be running from the top layer to the bottom layer. But in fact, that's our Y direction, so we need to create a coordinate system that we can use to define the direction and orientation of the composite. Now we could edit the material, but actually it's simpler to create a coordinate system. So coordinate systems, insert, geometry, click to change. Rather than use a geometry selection, we'll just use global coordinates at 0. But what we do need to change, we'll leave the x-axis as it is change to the z-axis to be vertical. Change default to geometry selection and choose that line, or that line if you like. apply. We've lost it. So now, in this particular coordinate system, the global one is different. Global says y is vertical, but the coordinate system we've just created has y horizontal and z vertical. So let's rename that so we know what we're talking about. Coordinate system for core. And then when we go to the core, we've not only said that it's honeycomb, but we can say use the coordinate system for core, so that we know it's now aligned in the correct direction. Connections. Promote to name selection. No, we want to rename based on definition, so we can see it's all bonded. Now we want the core to be bonded to the skins, so that's fine, but these, we're going to make them no separation. Mesh, what about mesh? Let's insert sizing of 0.5 and this insert sizing of 0.5 in the core as well, and then the skins will have 0.25. Let's see what that looks like. It's not bad. Let's change the names. So these are body sizing and the pins. Body sizing in the core. Body sizing in the skins. Always a good idea to name things. It makes it so much quicker to find things. Okay, so everything's named. We now need to constrain things and apply forces. So we're going to assume that the pins are held by the ends. So let's give you, we don't want mesh, we want static structural. We're going to fix the end of that. So we're holding the pins at the bottom by the ends, holding them still. Fix support. And instead of applying a force, we're going to insert a displacement. And we're going to allow it to move however it likes in the X directions and the Z directions, but on the Y direction tell it to go down 1 millimeter. So we're doing basically what happens in the test, where we push down in the middle. Now we also need to work out the symmetry planes, so let's have 1, 2, 3, 4. That's one symmetry plane with a frictionless support. Frictionless support, cross section, and another symmetry plane. Okay, 1, 2, 3, 4, insert frictionless support, 4 faces. Four faces and 4 faces. Okay. So that's our symmetry planes. that should be all set up. Solve, hope for the best. Well, that managed to solve. Let's actually have a look at the results. Insert stress von Mises. Wow, very high. Something went wrong there. Something went very wrong. We missed something, didn't we? Hold on. Frictionless support, longitudinal, we missed his face. Apply. Solve. Okay. Slightly saner results. And you can see that the different parts within this are experiencing different types of stresses. Let's which tells you that the stresses in the core are very low, but that doesn't necessarily mean anything. I mean, it doesn't tell us anything about how the core is behaving. Let's have a look instead at strains. So solution. Let's only look at this body. Insert strain. Let's look at shear strain in the XY plane. So there's a very high region of shear here. So that's where you would expect to see failure occurring because of shear of the material. Remember, this is a laminate structure. So the shear between the different planes is where it gets interesting. What else can we look at? Let's look at everything, but insert stress in the normal direction, but vertically. So it's fairly uniform stresses in the vertical direction, whereas there's quite an abrupt change when you look at the axial stresses. So let's duplicate this, change it to the x-axis, solve, and let's rename all these so we know what we're looking at. Now the x-axis normal stresses are basically the bending stresses, so you can see the bending in the top layer, the top skin and the bottom skin, and not so much happening in the composite core. The stresses that you see around here are actually wrong. You don't see that in a contact. That's basically saying there's a lot of high tension here. And as with the problem that we looked at with the hook, you don't see tension across contacting surfaces. You only see compression. You would expect to see a blue zone more or less where the blue zone is, but not to see the red zone there. Now, there's a lot of tension here, so the contact here is slightly odd. But getting contacts right in ANSYS is always difficult, or indeed in any finite element package. Something you can look at, if you want, is to select this surface, insert, stress, normal, Y, and just look at the regions where the contact is. So again, you have this strip of blue where you've got high compression and a strip of red where there's high tension. And the reason this is happening is that the pin is trying to stay in contact in a place where there isn't actually going to be any contact. So a lot of care needs to be taken to get the contacts right before the stresses will appear to be correct. But what we have managed to do is solve a beam in 3-point bending, or a short beam test even, with a honeycomb core. It's not the most sophisticated analysis, but it's a good start. I'm going to end on that note. If you're still here, thank you for listening, and I'll be back soon.